Have you ever wondered if a computer could truly think like a human? Not just calculate, but understand. This question is at the very heart of a new frontier in technology, neuromorphic computing. We are exploring the creation of brain-like computers, machines designed to mimic the elegant and efficient architecture of the human brain. This isn't about creating artificial consciousness in the way science fiction portrays it. Instead, it is a practical engineering challenge. The goal is to build processors that can learn, adapt, and process information in a fundamentally different way than the computers we use every single day. The journey is complex, but the destination could reshape our world. The core idea is simple, but profound. For decades, computers have followed a set path laid out by their programmers. They execute instructions one by one, in a linear and predictable fashion. This is known as the von Neumann architecture. So, what exactly is a brain-like computer? Think of it like building a city grid. Instead of a single long highway, in a standard computer, data moves back and forth along that central highway between memory and the processor. That creates a traffic jam, a bottleneck that slows things down and wastes energy. A neuromorphic computer is designed differently. It's like a sprawling city where memory and processing are intertwined in every neighborhood. Microchip nodes with local memory visuals. Each neuron in the chip has its own local processing and memory, removing constant data travel. This design is inspired directly by biology. Your brain is a vast network, roughly 86 billion neurons. Each neuron connects to thousands of others via synapses. When a neuron receives enough input from its neighbors, it fires, sending a signal onward. It's an all-or-nothing event. Neuromorphic chips replicate this with electronic components. They use spiking neural networks. Artificial neurons send discrete pulses only when a threshold is met. At their core, neuromorphic chips process information through events, not through a constant clock cycle like a traditional CPU. Think of it as communication by Morse code rather than a continuous radio broadcast. A standard processor is always running, always checking its clock, and always performing calculations, even if nothing new is happening. This is why your laptop gets warm even when it's idle. A neuromorphic processor, on the other hand, remains mostly silent. Its components only spring to life when they receive an incoming signal, a spike from another artificial neuron. This event-driven nature is the secret to its low-power usage. The architecture is also fundamentally different. Instead of separating memory, RAM, and processing CPU, neuromorphic chips co-locate them. Each artificial neuron on the chip has its own small piece of memory and processing capability. Comparing today's mainstream AI with brain-inspired neuromorphic AI is like comparing a meticulously detailed encyclopedia to an intuitive, adaptive student. Today's deep learning models, which power everything from language translators to image generators, are like the encyclopedia. They're trained on massive datasets and powerful data centers and become static experts on that data. They are incredibly knowledgeable but rigid. To learn something new, they often need to be completely retrained from scratch, a process that is both time-consuming and energy-intensive. Brain-inspired AI, running on neuromorphic hardware, is more like the student. It is designed for continuous, on-the-fly learning. It can adapt to new information without forgetting what it has already learned, a concept known as online learning. Looking ahead, the potential payoff for mastering neuromorphic technology is immense and deeply human. Imagine a world where advanced technology is not confined to massive, power-hungry data centers, but is embedded intelligently and efficiently into our daily lives. This is the future that neuromorphic chips promise to unlock. We could see prosthetic limbs that can interpret neural signals directly from the user's brain, allowing for fluid, natural movement, and even a sense of touch. They would learn and adapt to the user's intentions in real time, becoming a true extension of the body. Imagine tiny, implantable sensors powered by neuromorphic chips that constantly monitor your body's vital signs. They could detect the subtle early warning signs of a heart attack or a seizure and alert you or your doctor long before a critical event occurs. Because they use so little power, they could operate for years on a single tiny battery, providing a constant, intelligent guardian for your health from within. The promise is not a world run by artificial brains, but a world where brain-inspired technology helps each of us live healthier, safer, and more capable lives. The future of computing might just be more human than we ever imagined.